Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be talking about turbulence, in particular 1 and 2 equation closure models, and of course just mention higher order equation models. These are closure models using 1 or 2 or more differential equations to close the Rand's equations, which were derived, of course, in the previous class. Remember, the purpose of these models are to close the equations and that we need to make the number of equations equal to the number of unknowns. In the previous class, we looked at particular algebraic models. These are models that are perhaps seen as the zero equation models. We introduced the concept of Ludwig-Prandtl's mixing length hypothesis and reviewed the formulation of one of the most famous and historic models, of course, the mixing length model based on these Prandtl mixing length hypothesis. And we looked at this for the formulation for a boundary layer turbulent flow. Note that these models can also be used and examined for other types of flows. Then we reviewed 2 contemporary models which have been used a lot today, and they are the Sibecki-Smith model and the Baldwin-Lomax model. We looked at a few predictions of these for applications of boundary layers and separated flows. But of course, if they're operated outside their range of application, then they have very limited predictive capability. We finished off with another model, which was of course the King-Johnson model. And this was examined, and it might have similar shortcomings. Today, we'll try and expand our range of physics and modeling using all the concepts we've learned before in the module of turbulence of this class and on your equations in fluid dynamics. We'll be using dimensional analysis and some physical insight. So today, we'll look at 1 equation and 2 equation models in particular. We will try and derive the turbulent energy equation. We'll first look at 1 equation models, which have 1 partial differential equation in addition to the other equations and parameters to close the model. In particular, we'll look at 2. The very famous Baldwin-Barth model, the same Baldwin as the zero equation model we previously talked about, and the Spalart-Allmaras model, which is one of the most important models in CFD today. We'll also look at a number of other 2 equation models that have 2 partial differential equations to close the equations of motion. They're the K omega and K epsilon model. K is turbulent kinetic energy, and omega and epsilon are specific dissipation and dissipation respectively. These models came out of other famous theoreticians' work too. We'll also look at a few other particular closures, some particular closure coefficients. You can actually see the full set of equations that are being solved, and we'll discuss them, and we'll look at a number of applications and talk about their predictive capability. I think you'll be pleased with the results. Let's now turn our attention to the so-called 1 and 2 equation models. First of all, these are based on 1 or 2 partial differential equations, as we've mentioned before. They often use the same Boussinesq eddy viscosity approximation, which was used in the formulation of the zero equation models. Go back and review eddy viscosity approximation if you do not recall it. Now, 1 equation models will generally be based on the turbulent energy equation, which we'll show in this class, and will result in 1 equation for the eddy viscosity. 2 equation models are complete, that is, they do not need additional specification of the solution in advance of the CFD solver phase, and they will provide typically some kind of scale. It might be a length scale or its equivalent, like a time scale, and in addition to the eddy viscosity. In the models in this class, we'll in particular look at models which produce 1 equation for turbulent kinetic energy and the second equation for dissipation. Let's now look at the turbulent energy equation. This was developed to incorporate non-local and quantities and statistics. That's no longer 1-point statistics technically, and flow history effects in the eddy viscosity. So Ludwig-Prandtl also suggested this type of particular equation. He did this in 1945, and if you remember, he developed the boundary layer theory in the early 1900s. So he was a very active researcher in fluid dynamics over many decades, continually making excellent achievements, certainly worthy of the Nobel Prize. Now, the velocity scale we'll try and find for this particular equation will be based on the turbulent kinetic energy, TKE. Recall that TKE is nothing but the trace of the Reynolds stress, which we write here in this particular equation. UI prime bar. Remember, that's the autocorrelation of each velocity component in summation, otherwise known as the mean square velocity components, their summation to the half power. So that's an energy term. It has the units, of course, meter squared per second squared. Here, K we call the turbulent kinetic energy, and we'll informally call it TKE, K, or some variant of this in class, depending on the model. Now we can write the eddy viscosity as some length scale times the half power of turbulent kinetic energy times a constant. We introduced a very similar model in the previous class where we were discussing eddy viscosity, and we can produce the same type of model here. Of course, there's always the problem of finding some sort of length scale. And we also have to determine K through the code, but now I have to do it all simultaneously, because of course we're trying to find a solution. So one might ask, how do we determine K within a turbulence model? Well, one way might be to take the trace of the Reynolds stress. Tau II would be the negative of bar ui prime, which is negative 2K. So we found and formed previously a differential equation for the evolution of the Reynolds stress tensor. You might imagine that we can also find a corresponding differential or partial differential equation for turbulent kinetic energy by taking this trace of the Reynolds stress tensor. So please review the previous class and look at the derivation of the Reynolds stress equation. All we might do is take the trace of that equation across all terms, and of course then we would find the equation as partial differential equation for the scalar of turbulent kinetic energy, instead of course, a tensor equation. Now, for example, for incompressible flows, you might find this particular form of the turbulent kinetic energy equation. And it's put in a form, the terms are rearranged simply so that we can put it in a form which is similar to the other equations like energy, momentum, and conservation of mass. You'll see the first term is partial K, partial T. K is the turbulent kinetic energy, it's the energy of the turbulence. So that's partial derivative. It's an unsteady equation by definition. There's also a compressible form, which of course has a factor of U in it. A factor of density. And of course, the second term is like a convection term, and this would go as capital U. Remember, that's the average velocity at some point in space, times the partial derivative TKE with respect to x, y, and z direction. The other terms on the right-hand side, we give special names. Now here we see the introduction of epsilon, and it's a formal, not exactly the formal definition, but very, very close to it, which we'll discuss in a little bit. Here, epsilon is the dissipation per unit mass. That's the dissipation of turbulent kinetic energy. Note that, hey, this is a term that signifies the turbulent kinetic energy is increasing, and it's balanced by a decrease in turbulent kinetic energy. The other terms must mean somehow the energy is moving around or being changed in different ways, and we'll describe that physically in a second. Now, if you look at dissipation in its full form, you will see it's equal to a viscosity times the autocorrelation of partial ui prime partial xk, partial ui prime partial xk. Now you'll notice that there's two summation over two indices. Of course, in this particular equation, we would be holding I equal to 1, and then we would be summing over k equals 1 to 3, so there's really three terms. Then we would hold I equal to 2 and sum over k, and I equals 3 and sum over k. So you can see there's an additional, of course, 9 terms in total. Now let's look at the other terms. Remember, this is the rate at which energy is dissipating per unit mass, and it's only of the turbulence, not of the actual entire flow energy. Now, if we look at the first term on the right-hand side, right here, this is known as the production term. It represents the rate at which TKE is transferred from the mean flow to turbulence. You'll see it's a very interesting term because, of course, it has this shear stress term, but also there's a partial derivative with respect to x. So if this is a shear term, like say partial u partial y, that means that turbulence is being produced by that particular shear. Of course, there's viscosity in tau ij, and there must be a viscous term too. So this term here on the right-hand side is where turbulence is being produced. That's why it's called the production term. Oh, mind you, the second term on the left-hand side is just like a convection term. It essentially sort of moves the energy through the flow. Of course, the left-hand side can also be written as something like a material derivative or total derivative. All right, now, the dissipation term, which we already talked about, which is epsilon, is a rate at which TK is converted to thermal internal energy, and of course, a tiny, tiny bit of acoustics if it's a compressible flow. We're left with this third mammoth term, which we split into 3 parts, the first, second, and third. The first part, of course, is the molecular diffusion term. And you can look at this term and imagine why it's just like molecular diffusion. It's a diffusion of turbulence caused by the fluid's natural molecular transport process. And it's just like, in a similar fashion, of a form of equation of diffusion, which we looked way back in the mathematical review part of the class. Please recall that equation and its physical properties. This has a very similar form and it has very similar physical properties, and that's why it's called a molecular or diffusion equation. The triple correlation term, right here where my cursor is moving, is a turbulent transport term, and it's the rate at which turbulent energy is transported through the fluid by turbulent fluctuations. So indeed, the turbulent fluctuations themselves are moving additional fluctuations. This is the idea and the purpose, the physical interpretation of this term. Finally, there's a pressure diffusion term. Why is it called pressure diffusion? Because it causes the turbulent transport resulting from correlations of the pressure and velocity. That is, the pressure is also being very much diffused, just like the molecular diffusion term. Except, of course, it has different prefactors. One, of course, is the viscosity, and one, of course, is the inverse of density. But it's a very similar operation. Notice the sub j in the primes and p. So this is really a one-point equation and statistical term that involves the fluctuating pressure with each of the velocity components. Because of course this j here and j here are summed from 1 to 3. So notice that these all terms are summed out with index notation because of course there's two dummy variables, j and I. Anyway, that's the physical interpretation of the turbulent energy equation. And the more you use it, the more understanding you'll have of it. It's a physical interpretation of the balance of how the turbulence and its energy is transformed through the flow in a single equation. Of course, we'll have to model some of these parameters because they're not found directly as a particular field variable. In fact, once again, in some sense, we've introduced more terms which need to be modeled. What an excellent problem to deal with. Now, if you've remembered the definition of the true dissipation, which we discussed earlier in our mathematical review and equations of fluid dynamics, you'll note that the dissipation found from the turbulent energy equation is of slightly different form. Here, of course, the dissipation, which we write true, just on a temporary basis, will go as 2 nu sik prime prime bar, which we expand out to the right-hand side. These are basically coming from the definition of the Navier-Stokes equations. And this is for incompressible flows. If we compare a flow, say with a solution in CFD, and we can recalculate epsilon using its formal definition, can compare it to the one calculated in the flow, you'll see that it differs by approximately 1%. So there's a little bit of mismatch in the equations of motion for this case through this derivation. So this is a little bit frustrating, but nonetheless, we'll press forward with this tiny error involved in the dissipation. Now, the unstudied terms, the convection and molecular diffusion equations, thankfully, are all exact, and if we recalculate them, they'll have no error, both analytically and numerically. So, this also means, as you see, that they involve unknown correlations. For example, this triple correlation is absolutely unknown, and we would have to model it. So to close these equations, we must specify tau ij, the dissipation, the transport term, and of course the pressure diffusion term. That's now our major goal and hurdle to perform in the RANS closure for one equation and two equation models using the turbulent transport energy equation. So in this class in particular, we'll continue to assume that the Boussinesq approximation is valid, and therefore there'll be some specific Reynolds stress tensor. Tau ij will go as 2 nu tau, which of course is any viscosity times Sij, right up here except without the prime, minus 2/3 of turbulent kinetic energy times the Kronecker delta function delta ij. Recall that when I equals j, for Kronecker delta it's 1, and for I not equal to j it's simply 0. Let's try and continue with the Boussinesq approximation and assume that it's valid. We will assume that the gradients based on the diffusion are also, of course, valid for molecular transport processes. And we'll try and model our turbulent transport and pressure diffusion equations in this form. We'll write the summation of the triple correlation and the pressure diffusion term as a negative of the eddy viscosity over sigma k which is simply a coefficient for closure. We just add in a coefficient to calibrate, times the partial derivative of k with partial xj. So you'll notice that also this approximation and model, it's a model equation based on physical arguments and scaling arguments, which turns out to be an excellent model, will be, of course, dimensionally correct and fairly accurate for a lot of flows. Now, you'll see we still have made very, very little progress in our modeling effort, and we absolutely still have no knowledge of the local length or dissipation scales, but we gave you clues on how they might be found in the previous classes. We've already used, based on dimensional grounds, one way to estimate the dissipation with length scale, which epsilon will go as k to the 3/2 over L, and k would have units of meters squared per second squared, L will have units of meters, and epsilon has units of meters squared per second cubed. You can check the units yourself, but this is just a dimensional argument, and you see it's an approximation. Now, using these two particular approximations, we can rewrite our differential equation for the turbulent kinetic energy, that is the turbulent energy equation, as the basis for almost all higher order, that is first equation and higher order turbulence models. Rewriting our equation from the full form that's formal here on the top of 6 all the way to bottom of 8, we'll find partial k partial t plus uj partial k partial xj. The left-hand side's unchanged. The first two terms are unchanged, tau ij partial ui partial xj minus epsilon plus partial xj of now the viscosity plus the eddy viscosity divided by sigma k partial xj, which is up here. See how that's substituted. Very simple and straightforward. Now we can try and close this. And we might be curious and use one of the simplest models, of course, which was originally proposed by Prandtl. Here's this equation. Now we can write epsilon equals CD, where CD is not really a coefficient of drag, it's just a coefficient which Prandtl wrote. Unfortunately, there's some similarity, but we'll use the same variable to honor the history of the subject. Times turbulent kinetic energy to the 3/2 divided by the length scale. Now, we'll still be able to calibrate C sub D later. It would be good to find an approximation as the production would be proportional to the dissipation. If the production of turbulent kinetic energy, that is the rate at which it is created, is equal or proportional to its dissipation, that is the rate it is destroyed, then we can simplify our whole model now. And we'll do that in Prandtl's first one equation model, which represents, of course, really one of the first one equation turbulence models, which was very popular, although it's not very much used today. It's based on the same idea as, of course, the mixing length turbulence models. And it also is based on the core idea of turbulence being in perhaps a cascade, which wasn't really known to Prandtl at the time, because he was in Germany and the Kolmogorov was in Russia, and the Russian school certainly didn't talk to the Germans in 1941 to 1945 as it was World War II. But the idea remained nonetheless that there was a balance of energy in a flow. And Prandtl, I do not believe, thought that this balance was generally interrupted. So he conformed with these assumptions and these equations, Prandtl's so-called one equation model. And here it is, which I've written down here. Here the eddy viscosity goes as k 1/2 L, and of course that would also be equal to CD k squared over epsilon if you're combining the two equations we just introduced. Simplifying the turbulent energy equation, that is the equation for turbulent kinetic energy, we'll have the same left-hand side. We'll have tau ij of partial u partial xj, so that's the same term. And then, of course, we lose that dissipation term, and of course, all the triplets and difficult terms of the model on the right-hand side are gone. So now, really, what don't we know in this equation? We don't know k, but that's the equation which is representative. That's the variable we want to find. It's now a field variable, the turbulent kinetic energy. We don't know the mean values u bar, but those, of course, are shown in the momentum and continuity equations, etc. We don't know tau ij, but that's just stress tensor. It already appears in previous equations. CD is a constant. L is a length scale, which we likely don't know. K to the 3/2 is, of course, turbulent kinetic energy again, and we know that viscosity will be a constant, and the eddy viscosity, of course, we have another equation for. This is an algebraic equation, which is in addition to this partial differential equation. So when we add up the number of equations for turbulence closure, we're really only adding the partial differential equations, not algebraic equations. Then we have, of course, sigma k, which of course is another constant. So really, there's only a couple constants and one really variable that we don't know, plus L. But of course, we have another equations for L. So we really have one PDE and one algebraic equation here, if I'm counting them correctly. So this represents the first one-equation turbulence model that's generally accepted in history. Now, that was the first model, and of course in practice it wasn't that predictive and accurate relative to experimental flows, but nonetheless it has been studied extensively for decades, and one of the most popular and accurate models, which was in heavy use for a long time, was published and created and given to our world of fluid dynamics in 1990 by, of course, Baldwin and Barth. The Baldwin-Barth model today is less popular than it used to be in the 90s and 2000s. It's been replaced by more advanced models, but it's still in use in many codes. It is one popular one-equation model. It contains exactly 7 closure coefficients and 3 empirical damping functions. So just like Prandtl might have developed the zero-equation model, also, and people came along and modified it, as we've seen in the previous class, people have taken the idea of the one-equation model of Prandtl and have modified many of the terms and added empirical functions. It is and represents a simple implementation compared to more complicated models. So there's much more complicated one-equation models. The good thing about the model is that there's absolutely no requirement to specify the length scale L. In the zero-equation models, we had to specify some type of scale. Here, L is found through the equations in motion, and we do not have to specify in advance what that particular value might be. We also would define the eddy viscosity would be modeled in terms of spatial gradients, which is of course the model proposed by Baldwin and Barth right here. You'd have to pull their paper from Google Scholar to see the full development. One unfortunate thing about these particular models is it does not allow the turbulence to dissipate when no gradients exist. This is a completely unphysical thing, and it caused many problems. So you see, with this particular form, if these partial derivatives, say, amount to 0, so 1 over sigma epsilon, this is just a constant, is a constant. Partial of the eddy viscosity with x, if that term is 0, that means that the eddy viscosity is relatively constant in the flow. That means we have uniform turbulence in the flow. There's no gradients of turbulence. And, of course, if the viscosity times this factor, our tau, is, and of course, if this term, partial nu, our tau, partial xk is 0, then if any of these are 0, in any of these cases, then epsilon would of course be 0. That means if we just have a turbulent field, it would not be able to dissipate. This is completely unphysical. Remember, in the theory of Kolmogorov and just experiments where we take turbulence in a room and stir it all up. For example, if we have a ceiling fan on in a room and we turn it off, the room's in turbulence, but then it'll decay and become quiescent. There'll be nothing to force the flow. All that turbulent kinetic energy will be dissipated by the viscous forces and become a quiescent environment. If you use the Baldwin-Barth model for that particular situation, it will fail because, of course, all these particular gradients are going to be 0, and there'll be no mechanism to dissipate the turbulence. Let's now look at the particular equations and describe them in the Baldwin-Barth model. So if your CFD code uses this model, these are likely the exact equations they're solving. Let's look at them now. First of all, there's the kinetic eddy viscosity term. You can see they've modified it from the one we proposed, but it's really the same. The eddy viscosity will go with some coefficient, which they call C mu, they can call it whatever they want, times the viscosity, times this term RT, which is like a turbulent Reynolds number, and 2 coefficients, d1, d2. You can see all the closure coefficients and relations of Baldwin-Barth's paper we have listed down here on the bottom of page 11. There's a lot. Some of them are actually forms of partial differential equations, which are closed, and some are just constant coefficients. But you see, this is one particular algebraic equation. The turbulent Reynolds number equation is a slight modification. It is not now tracking, of course, turbulent kinetic energy. It is now tracking turbulent Reynolds number. So you can see Baldwin and Barth have transitioned from the use of TKE tracking to the turbulent Reynolds number itself. This is a brilliant idea. And there's many models and variants of their models. This is why I'm actually showing it in the introduction to CFD, because it was such a landmark idea. Today, of course, there's modifications of the landmark Baldwin-Barth model that have different closure coefficients and empirical functions, and of course modify this form so that the energy can dissipate. You can try out these models in some popular CFD codes to see for yourself. Let's now turn our attention to one of the most popular models, the Spalart-Allmaras model. Today, Spalart is working at Boeing as a Boeing Technical Fellow as the time of the making of this video. His colleague who created the model with him, Allmaras, also works in Seattle through the MIT lab. They're both active turbulence researchers, and their names are internationally famous in the fluid dynamics community because of this particular model. It is a one-equation model, and as you imagine, it is not particularly tracking turbulent kinetic energy or Reynolds stress. It is likely the most popular one-equation model in existence, and for that reason, we'll be trying it out in our classes. It is indeed an industrial workhorse that is widely used for RANS closures in industry, and Spalart, of course, is actively developing the model. It is used today for full aircraft safety prediction, so it scales really well. It's an excellent model for those types of large-scale, complicated turbulent flows. It is the basis for a combination of advanced turbulent models that will be discussed later. It's also considered a complete model of turbulence because all the scales of turbulence are automatically defined, that they're not specified necessarily in advance. Now, Baldwin and Barth tracked the turbulent Reynolds number. Prandtl-type models, for one equation, tracked turbulent kinetic energy. The brilliance of the Spalart-Allmaras model is they developed a single equation, partial differential equation, that tracks eddy viscosity. And here you can see it in the familiar form. Here we have a partial derivative of the eddy viscosity, with it written as a tilde with time, plus u of the partial eddy viscosity partial xj equals all the terms on the right. You can see that they use some of the similar approximations for particular terms, just like the models that followed Prandtl. This term here should look very, very familiar to you now, because of course it was developed in this very class. The other terms, of course, are connected to closure coefficients, which are all listed down on the bottom of this page. Take a few minutes to study this particular model to fully understand it. Now you'll see they have a kinetic eddy viscosity. This is a core idea in the model. And of course, this represents an algebraic equation, which is being solved during the solver process. The eddy viscosity, which they write with a tilde, times this function f sub v1. Now if we look up s sub v1, it's down here in the closure coefficients, which represents another nonlinear algebraic equation. And it goes as this script x cubed over x cubed plus CV1. CV1 here is 7.1 in their calibration over a wide range of turbulent flows. Then you might say, okay, well, what's x? Well, x is down here. It's the ratio of nu tilde over nu. So that's well and good. That seems to be kind of closed in its sense, in itself. But then if you look at their partial differential equation, which is their one equation, that is in the one equation model, you'll see that there's many other types of coefficients and terms. You can track these down here. So technically, just taking this page and the RANS equations, you have all the equations you need to program them in a particular CFD code, and of course, solve them. The model's closed. And of course, there's a huge philosophical and mathematical and physical arguments in the formation of all these empirical terms, their calibration, along with this single equation model. You can imagine it took a physical insight developed over a career to create a model like this, to model the dynamics of turbulence, which essentially nobody really understands at a deep level mathematically or physically. Let's now turn our attention to the two-equation models. Now, two-equation models are most often used as two linked partial differential equations. The first is often turbulent kinetic energy, and the second one varies. But typically, the second equation is either the dissipation or specific dissipation rate. That is epsilon or omega. There are many, many, many choices for what the two equations are. Just as we saw in one equation models, there's many different choices. We could, for the variables being solved, we can choose any two particular variables we wish for the two equations. But of course, there's popular choices which are implemented in the CFD codes. They all have in common two differential transport equations of turbulent quantities. There's always a debate within the community regarding what the second transport differential equation might be. Most agree that the first equation should be TKE, that is, the turbulent kinetic energy. So if you go to a turbulence modeling conference today and you go to the RANS-based sessions, you'll likely hear arguments about which equation's the best, even today. There's likely no best answer. There's probably a particular set of equations for a particular flow which is the best choice. Now, these two equation models, thankfully, are complete, and they have no knowledge of the turbulence of the particular structure typically, because of course they're one-point statistic models. That may not be true for more advanced models, which we'll talk about later. They typically also use the Boussinesq approximation, which we've already talked about. Andrei Kolmogorov, the great academician who started the Russian school of turbulence, created the first two-equation model of turbulence through the turbulent kinetic energy and the dissipation rate per unit turbulence. So when you see models that are called K omega, you should know that you're using a model which developed in the so-called Russian school. This is opposed to the one-equation models which were developed in the German school, which was created by Prandtl. It's a little bit funny and historical that two excellent researchers in the field were in two different countries and had very little communication or knowledge of each other. And of course, they had developed two major theories of how to do the Rand's closures of the turbulence problem. Let's look at these particular two equations models now. Historically, nobody really knows how academician Andrei Kolmogorov found the first two equation model. But let's just perhaps do a little bit of theoretical work, or hand-waving, if you will, on physical and dimensional arguments to understand this. We've written this particular argument here for you on page 15. If the eddy viscosity goes as the turbulent kinetic energy, which we've done earlier, then the dimensions of the eddy viscosity will be length squared divided by time. We also note the dimensions of turbulent kinetic energy are length squared per unit time. Therefore, the turbulent viscosity divided by turbulent kinetic energy will have dimensions of time. Therefore, the turbulent dissipation has dimensions length squared per time cubed. We actually all know these things, but we can prove this and show this through those arguments. Therefore, the dissipation divided by turbulent kinetic energy will have dimensions of 1 over time. This makes sense, therefore, to introduce a variable with the dimensions of 1 over time, which is omega. See, if we're interested of the form of epsilon over k, we should have a corresponding variable with the same dimensions of 1 over time, which would be dissipation. We've also shown through this physical argument that dissipation, omega, will be related to epsilon. Of course, omega is just a per unit second time scale. Now, Kolmogorov postulated through his work the following partial differential equation for omega. And we don't use this particular equation in contemporary CFD, but all the K omega models are essentially using this philosophy and approach. Kolmogorov, in his paper, wrote that partial omega partial t, that's the specific dissipation, will be plus its convection term will be equal to a right-hand side of a negative beta omega squared plus partial xj of sigma times eddy viscosity of turbulence times partial omega partial xj. This is a very simple and elegant differential equation compared, of course, to the previous ones we've looked at. There's only two terms on the right-hand side. You'll see that this term, this equation, in one set contains everything we need. It contains the unsteadiness, the convection, the diffusion, and the dissipation and dispersion and production. We can use more modern forms of this equation, which we will show shortly, and talk about their development and use. But you'll see that's all that's missing in there, really, this equation is the so-called production term. And that can be, of course, added. Now, omega might be seen as, if you interpret it physically, if you have no physical idea what it is, as a frequency characteristic of the turbulence decay process under its self-interaction. Think about this careful quote created by and written down by Staffman in 1970 in his interpretation of omega-based models. Let's now look at one of the most popular K-omega models. This one's developed by Wilcox, who's a famous researcher in contemporary CFD and turbulence. We'll simply write down the major equations for you. As before, we had an equation for turbulent kinetic energy. This is essentially exactly the same trace of the Reynolds stress equation, and we get an equation for turbulent kinetic energy K. This is one particular PDE that's being solved in the two-equation solvers. Remember, two-equation models and closures have two equations. Of course, the second equation will be omega. This is the equation for omega. It has almost the same exact form. It's a beautiful set of equations. You can go down and compare each term side by side and see the differences, and they're almost being tracked exactly the same. This is rather elegant too, because in the CFD code, you have to calculate many partial derivatives. You can exactly use the same discretization scheme and grid for these types of variables, just but just replace k with omega for each case. It saves on programming and implementation. I believe that this is by design too. Based on these two equations, and of course the single algebraic equation for kinetic eddy viscosity, which goes as k over omega, where omega is a specific dissipation, k is turbulent kinetic energy, we'll have these particular closure coefficients. So for example, alpha and beta, beta star, sigma, sigma star, these are all basically constants or simple algebraic equations. More constants, more physical functions. These are all shown, and some are very typical and used many times in CFD for advanced models, and of course some are much simpler. You can see we can even recover a length scale if we so desire, which is the integral scale of turbulence, or a very large scale. It goes k to the 1/2 over omega. now shown the basic mathematical operations to derive the epsilon equation and the standard K epsilon model. Let's look at their form now. The kinematic entity viscosity will be nu T equals C mu of K squared over epsilon. So this is again the eddy viscosity term, turbulent viscosity, and it goes as a constant, which is universally called in the community of C mu. It's almost 0.09. You saw that coefficient come up 2 classes ago, in fact, and it came out of theory. Nonetheless, K squared and epsilon remain, turbulent kinetic energy and dissipation. Now, our two equations, our two additional PDE beyond the Reynolds average and average Stokes equations, are for K and epsilon, and we've already talked about these. You've seen now that they have reduced through many physical arguments and a lot of research, which we can review if you so desire in class, the coefficients of epsilon in this form. So it's greatly simplified, and you see it's put in a form with 3 terms on the right-hand side for K and epsilon. And this is done for practical purposes, just like the K omega models of today. There's also standard closure coefficients for the so-called standard K epsilon model. Here they are. These were found through a combination of theory and comparisons with experiments. This model was published in 1974 by Launder and Sharma. Launder, of course, was a professor, and Sharma was his student researcher. Those are the standard K epsilon model. You imagine that there's many derivations and variants of it, and we'll be showing some of those in class. It's very unlikely you'll be evaluating models like Launder, Sharma in your CFD codes. You'll see there's very complicated and contemporary ones which are better in predictive capability, like the Chien model. We'll look at that later. And we'll run some of these models in class. Now, most of these 2 equation models, as you've seen, involve 2 or 3 variables, K, epsilon, and omega. Epsilon and omega are very closely related because one's just the specific form of the other. Nonetheless, they're derived in completely different ways. It should be mentioned here that there's many other types of models, and they just choose other variables for the governing partial differential equations. Here's 3 particular examples. One might be the product of turbulent kinetic energy and the integral length scale. This is a famous model made by Rada in 1968. It just goes as KL instead of K. It's shown in the lower left. Here's a PDE for KL instead of just K. That would be like Rada's model. Another one might be the integral time scale. For example, instead of tracking integral length scale, we might look at the integral time scales of turbulence and track those with a PDE. That's in the lower right. You can see we have a material derivative operating on integral time scale. We can also choose basically any other quantity or statistical quantity of turbulence we desire and create differential equations for them. And over the course of many decades, people have created all these models. It's probably bewildering to you as someone new to the closure problem of turbulence. There's no truly right answer, and there's many arguments in the community about which one's best. And I can tell you there is no best model right now that's not universally agreed upon. Typically, certain models will be used for certain jobs. In particular, for a field like aeroacoustics, there's particular turbulence models which were just created just for the field of aeroacoustics. Let's now turn our attention to the ideas of the closure coefficients. You'll see that all these models worked hard to develop 1 or 2 additional PDEs, and they have corresponding closure coefficients. We can essentially choose any coefficient we want, unless it's one that comes out of the theory, which we're applying it from. And these often replace unknown double or triple correlations so that we can reduce the number of variables in the flow. And they're often written as algebraic expressions involving the known field variables and turbulence statistics which we're tracking with the 2 additional equations. Now, for example, in the K omega model, we saw a particular set of coefficients, alpha beta, beta sup star, sigma, and sigma sup star. These were found through a combination of theory and calibrating that code against experiments and known analytical solutions to find and calibrate those coefficients, of course. Many of these coefficients and the algebraic models replacing them, and we could talk about this at length, have been replaced on dimensional arguments and scaling laws. So we're setting these models and coefficients so that the predictions match basic experiments like shear layers, boundary layers, wakes, turbulent jets, backward-facing steps, and these are the types of flows we'll focus on in this class. Remember, if you can't predict a turbulent flow of a basic boundary layer, you'll be hopeless when you try and predict a flow over something more complicated, like through a heart or over a wing of an aircraft. Now, we'll show, in particular, how we find particular K omega model with the process, and it's the same for all other models. Looking at the K omega model, which we just produced, we will try to establish the ratio of beta naught and beta naught sup star through the application to decaying isotropic homogeneous turbulence. We previously discussed decaying homogeneous isotropic turbulence. Remember, homogeneous turbulence is where the statistics don't change in space, and isotropy is where the turbulence statistics do not change with rotation. We know certain statistical quantities to be factual and true through the theory that came out of the Russian school. And of course, more contemporary theories out of the United Kingdom and the United States. Here, we can write down some of these relations between how turbulent kinetic energy is balanced, that is, its rate of change, with the destruction of turbulence and its dissipation. Through that theory, we can write down these two simplified partial differential equations for turbulent kinetic energy and, of course, specific dissipation. For example, the time rate of change of turbulent kinetic energy at any point in the flow must be equal to, for high Reynolds number of homogeneous isotropic turbulence, the negative coefficient beta naught sup star of omega k. A similar equation is written for omega. These other coefficients in the equations are set to 0 because they cannot be terms which have any physical meaning in this balanced flow field, where of course the rate of change of energy is equal to its specific dissipation. And of course, through these three equations and the fact that script x must be 0 for k and omega in the equations because those terms are 0, we'll find and close part of the model analytically, which is f beta star and f beta, which must be 1. Through these equations, now we can argue, and the original k omega equations, that the turbulent kinetic energy must go as t, it goes, not equal, it goes at time to the negative beta naught star over beta. It turns out that if we match through theory the decay of TKE with time, then beta must be exactly and analytically 5/4. This matches experiments of grid turbulence, which is a form of homogeneous isotropic turbulence in local regions. Remember, physically, it's impossible to create a truly homogeneous isotropic turbulent field. It is theoretical. However, that being said, in certain regimes of turbulence, in certain localized areas, you will find regions that exhibit the properties of homogeneous isotropic turbulence. And so we can find this and validate it experimentally. The values of alpha and beta can also be found by examining the boundary layer log layer. So for part of the calibration of the standard K omega model, we've looked at Kolmogorov type theory. Now we look at the theory of the composite boundary layer turbulence to close the other coefficients. In a boundary layer flow, we might look at, of course, the inertial range. That's the range where, of course, the log layer is valid. And we'll put in our equations with our currently found coefficients and simplify them, and we find this set of particular PDEs. But what do we do that? This is also a system of equations, and it has a particular solution which is consistent with the law of the wall. But that's by design. We've put the equations and filled in the parameters and variables to, of course, correspond to the log law region. And of course, we can impose a profile, the composite profile which we previously developed, which will go as Utah, the friction velocity divided by 0.41, von Karman constant, times the logarithm of the distance to the wall plus a constant. Now we can fill in, of course, k and omega based on these values too. Now, based on these values in the log region and these system of equations, we can find the coefficients of beta naught star, beta naught over beta, so it's 5/4, which you already have, and beta. And so now we found beta naught star and beta themselves, not just their ratio. We need to find and close further coefficients. You'll see that in the viscous layer of the boundary layer and the defect layer, which represents the outer layer, we would have to follow the boundary layer profiles of the flows, and we must also select, and there's no other solution, of sigma star is 1/2. We can then look at the defect layer of the boundary layer corrections of Coles and find that alpha is 13/25. This is a very complicated process which would take a lot of time, but you're welcome to try and repeat this process yourself. But it will be a significant time investment for you. Alternatively, you can look up some of the papers I referenced and see the development of every step mathematically yourself. Nonetheless, for a K omega model, you will summarize and find these basic closure coefficients through a combination of theory and comparing with composite profiles of turbulent boundary layers. This represents the most basic example of the closure coefficients for the K omega model. Other excellent models use similar approaches of known theoretical quantities and flows and known flows from boundary layers, or calibrating the coefficients directly with measurements from experiments. Now, we have used our most basic approach for decaying isotropic turbulence in the fully turbulent boundary layer. That's troubling because, of course, if we apply our model outside those particular ranges of fully developed flow with high Reynolds number, then the model will likely fail. And so more and more empiricism is added to these models through additional functions to try and handle a larger range of flows. There are many other types of approaches, of course, to find these coefficients or alternative coefficients. For example, one might look at a separating boundary layer flow, a channel flow. They might use more complicated types of models like large eddy simulation, which we'll talk in another class. And they might also try and perform mathematical techniques like asymptotic solutions. You will see that for specific flows and for selecting closure coefficients are always a choice for the researcher. In fact, you might have the same turbulence model and use different closure coefficients and constants for different types of flows. For example, I could take the K epsilon model and use a different set of coefficients for a jet versus a boundary layer. This is not uncommon, especially in industry, though it's a little bit of an additional empiricism. In some sense, some people might argue that you're actually doing empirical fitting, which is not a very nice compliment. Anyway, ideally, we would use the completely different flow for each closure and have one set of coefficients. Remember, multiple closure coefficients are common in industry, but there's certainly a lack of elegance through that particular approach. It's not truly a predictive model. Let's now move on and look at how these results might appear for different types of flows for different kinds of models. Let's look at two models first, which we examined. We first examined the Baldwin-Barth model and then the Spalart-Allmaras model. We'll look at two models, the Baldwin-Barth model and Spalart-Allmaras model, which we just looked at in this class. The first column is the flow. There's a wake flow, a mixing layer, a plane jet, a round jet, and a radial jet. So we're looking at three types of jet flows, one mixing layer flow, and one wake, which is far down from a bluff body. Now, the Baldwin-Barth model is not predictive for these last four classes of flows, unfortunately. But it did produce a result for the far wake. In the last column, we've made measurements of particular quantities. If we look at the error of a boundary layer flow, we might vary the pressure gradient as we did in the previous class for zero equation flows. So a favorable pressure gradient is where, of course, the pressure decreases as you go in the downstream direction. The strong adverse gradient is where the pressure increases as you move with the flow in the downstream direction. There's a number of flows here, and they're just coded by set point. Now here's the percent error for both these models. You can see if we add up the error, average the error for Baldwin-Barth and Spalart-Allmaras, you get 25.8 versus 7.4. These are the type of comparisons one makes with the so-called one equation or two equation or all kinds of different models. There's many interesting competitions where people try and compare their turbulence closures to find particularly the best one for particular flows. Ideally, you want to create a single turbulence model which is predictive and have low error for all flows, but this is often very difficult to do, and people have spent their lives trying to create these types of models. Let's look at additional comparisons of course, the Baldwin-Barth model and the Spalart-Allmaras model. These are, of course, one equation models, and we'll look at it for boundary layer flow again, and we'll look at skin friction comparisons. This is just like last class. On the y-axis, we have skin friction. On the x-axis, we, of course, have spatial position on a fully turbulent boundary layer. The top row is zero pressure gradient. Then the next row is a mild pressure gradient. The following row, the third one, is an adverse pressure gradient. And finally, there's a strong adverse pressure gradient in the bottom. You can look that they both do very well for favorable pressure gradients, but when there's an adverse pressure gradient happening, you'll see that the Spalart-Allmaras model has a superior predictive quality. In fact, in the last case, where we have a very, very adverse pressure gradient, the Baldwin-Barth model is not even predictive relative to experiments, which are dots, and the Spalart-Allmaras model actually captures the right trend. It's just off by a factor of about 1.5, which of course is huge for skin friction, but this is a very, very difficult case to predict. Let's look at some more one equation comparisons of the separated boundary layer flow. Now note, neither of these closures were necessarily, at least traditionally, for separated flows. Nonetheless, there's more advanced forms than we showed today of the Spalart-Allmaras model, which tries to account for many of these types of physics. And those are really what's programmed into your CFD solver. When you run the Spalart-Allmaras solver, remember, this is essentially the types of results you're creating, with the Spalart model at least. On the left, we have a skin friction, and on the right, we have pressure coefficient along this particular backward-facing step. The flow moves from left to right. There's a shear layer on the top of the tunnel, and here's the backward-facing step of height h. Now they're making the measurements along the base of the backward-facing step. They've normalized the results by the step height h. The distance x goes from, of course, the position of the step downstream. For positive x over h, or x over d in this case, they're showing the results downstream of the step. So that's what on the x-axis. Experiments of driver are shown as circles. Now the two predictions of Spalart-Allmaras and Baldwin-Barth using the Rand's closure are shown as lines and dashes. You'll see in this case that they're both rather predictive, but Spalart-Allmaras seems to do better overall. Neither one predicts, and they're both relatively the same for pressure coefficient behind, of course, the step. So overall, they're both relatively well predicted, but the Spalart model is slightly better in terms of its predictive accuracy of the skin friction. Let's look at the Spalart model for the backward-facing step again. Of course, here's the same data set just for the Spalart model. In the lower part of the figure, you see contours of the Spalart-Allmaras prediction. And these, of course, can show that there's a recirculation region right here behind the step. This is where the flow reconnects and becomes attached again. So it goes from attached flow that's fully developed and turbulent within like a duct. It goes over the backward-facing step, and a circulation regime happens, and it reattaches. You can see this in the skin friction plot here. Here, of course, it's 0, which is where my cursor is now. There's where the skin friction takes a drop down because of this step, and then at the wall here, which is down here at the base of the wall, it'll have a large drop, and it'll come up again and be reattached at about 10, which is about where my cursor is here. So we can interpret both experimentally and with CFD what's happening exactly in this particular case. Let's now look at some experimental errors for particular two-equation models. And I should mention here that there's different kinds of models. This is a standard K omega model, this is a standard K epsilon model, and here's the so-called RNG K epsilon model, which is a modification of K epsilon. And we look at particular flows, far wakes, mixing layers, and 3 types of jets. And of course, we're looking at the particular measurements and ranges of measurements and comparing them with the results. For example, the far wake co-omega model gives a measurement of 0.339, the measurement is 0.365. K epsilon and RNG K epsilon are 256 and 290. And you can make these comparisons for all these flows for each particular type. You can kind of assess their predictive capability and accuracy. But do not discount K epsilon models just from this chart. There's other types of flows where they're going to be superior. And you'll have to make the best modeling choice for the particular flow you're trying to model. Let's look at another example. Here's the 2 equation models for pipe flow. Here the Reynolds number is constant, and we'll show comparisons of various statistical quantities. Here, of course, we're comparing the predicted with CFD and the measured pipe flow properties at a Reynolds number of 40,000, dependent on, of course, the diameter of the pipe. The solid line is a K omega model. The dots are measurements of Laffer, and the squares are measurements of the so-called Prandtl correlations. Now, you can see for the velocity profile in outer coordinates, it agrees fairly well for the K omega model, and with Reynolds number, if increasing Reynolds number, if we vary it with skin friction, it captures the trend. Anyway, take a few minutes to look at these different quantities. You can see we can recover Reynolds stress, which is well predicted. This is, of course, the distance from the wall to the center of the pipe. And then here's the Reynolds stress, which we normalize by the friction velocity squared. We've looked at these exact type of plots when we were talking about turbulent boundary layers. I'll let you look through the rest on your own. One particular one to take some time to look at is the production plot. For example, on the x-axis, we have friction velocity times the distance to the wall divided by viscosity. On the y-axis, we have production and dissipation. Remember, production is the rate at which the turbulent kinetic energy is being created, and dissipation is the rate at which it's being destroyed. You can see as we move away and increase the distance from the wall, that we will indeed have almost a balance between production and dissipation. So you can see even if this pipe flow, which is an anisotropic, inhomogeneous turbulence, the rate of production of turbulence and dissipation are relatively equal. So even though it's not homogeneous isotropic flow, that assumption in the closure coefficients wasn't that bad. Let's look at another two examples for the two equation models. In this particular case, we've looked at skin friction for a flow past the famous backward-facing step. We look at the k-omega model of Wilcox. Wilcox's k-omega model is in many contemporary flows. We also look at a k-epsilon model of standard form. And we're looking at the same data set of driver. This is published by, of course, Florian Mentor's work, who's another famous researcher in turbulence. And we'll use Mentor's turbulence model in our class. It's called the Mentor SST model. On the y-axis, we have skin friction. On the x-axis, we have x over h, the same backward-facing step problem. I'll let you take a few seconds to look at the comparison between the two models and the predictions. They are very predictive, especially the Wilcox k-omega model. In this case, it's done very well. We now need to take a moment and look at boundary conditions. For every one of the turbulence models in Rand's equations, we would need to have corresponding boundary conditions of turbulent kinetic energy, dissipation, specific dissipation, length scales, time scales, depending on the two equations being solved. Remember, we have to specify boundary conditions on the boundaries of our domain so that we can specify what kind of turbulent kinetic energy is entering the flow field, what kind of dissipation. This means we would have to add in and create all new boundary conditions for every types of turbulence model, and they'll all be unique. So just because we found closure coefficients, that is only part of the problem, and we would have to spend a lot more time developing every particular boundary condition. If you desire, we can talk about these more in class, but generally they follow the same philosophy of the eigenvalue approach. That is, if all the eigenvalues are positive, for example, then all the flows entering the domain in the supersonic, and we would have to specify every unknown variable at the boundary. That's just one example, which is the most simple. Also, at boundaries with walls, we would have to say the turbulent kinetic energy goes to zero. By definition, the velocity at the wall would be zero if it's a no-slip condition, and all the components of the turbulence would be zero at the wall. There'd be no dissipation at the wall either, because of course there's nothing to dissipate. Now, notably, at the inlet boundary conditions, we would typically have to specify incoming turbulent kinetic energy and perhaps dissipation based on the energy and some length scale. This can be very difficult. Remember, the specification of the turbulence quantities at the boundary will completely change your solution. So you can always use some default values of your solver, but I recommend thinking about the incoming turbulence to your domain and specifying it. Remember, if you do not know those values, you'll have to estimate them. And you might have to even use trial and error to select different turbulence quantities at boundaries to get the solution of physical characteristics you desire later on. So that can be a very difficult thing to do, and it can only be found with a little bit of experience and hopefully some insight into the flow through measurement or a flight test. Let's recover what we did today. We talked about a lot of new material, and it's probably good to review this class carefully. First, we derived the turbulent kinetic energy equation through the trace of the Reynolds stress equation. This is the basis of all the K models, of course, of single equation model, and of course two equation models. You usually use K as the first equation. They're the most common and what you'll almost always see in commercial and production codes. We then discussed two of the most popular one equation models. We also discussed two forms of two equation models. With one of those models, we showed one particular closure, of course, of the standard and traditional K-omega model based on theoretical results, which we showed in previous classes. Then we found and discussed how the closure coefficients are found for other models, and we talked about boundary conditions briefly. So we've shown some of these results of one equation, two equation models just to give you an idea of their predictive capability. But remember, the models will do better for certain situations, especially if they've been calibrated for them. Generally, I do not prefer that anybody chooses specific calibration coefficients, because of course it amounts to doing a type of empirical fit of the equations of motion and their solution onto a particular flow. That is a dangerous approach, because when you take those coefficients and apply them to other flows, they will certainly be less predictive than a general theoretical formulation of the closure coefficients. Next time, we'll look at compressibility effects. That is, mainly through this point in the turbulence modeling part of the class, we have not considered compressibility. This is very difficult in itself, especially if you haven't had any background in compressible flow. We also have to consider the effect of compressibility on turbulence. There's a difference between compressibility of flow and compressibility on turbulence. We could have a compressible flow, but the turbulence, which is its own characteristic of the flow, will not be compressible unless we do very high Mach numbers. And we'll talk about physical considerations, and then we'll introduce the whole new idea of the so-called Favre averaging, named after the mathematician Favre. And we'll derive the Favre average equations. These are opposed to the Rand's equations, but many turbulence closures and solvers today are actually solving as the base equations the Favre average equations. That just means they're mass weighted, and if you have a compressible flow, this is very ideal for the purposes of turbulence modeling and finding realistic solutions. We'll look at one particular compressible flow closure, and we'll apply that, of course, to mixing layer compressibility corrections and look at some particular applications. Thank you very much for your time today. I'm Professor Steve Miller.